As we heard, the first law of thermodynamics is a version of conservation of energy. Whatever energy you start with at the beginning of a process, you end with at the end of the process. And so what we need to really concentrate on is how this energy is transferred. We need to separate the system from the surroundings. Energy may transfer from the system to the surroundings, or may transfer from the surroundings to the system. The energy itself is what we're focusing on, not the types of the energy. And it's the relationships between the energies at the beginning, the reactants, and the energies at the end, the products, that are going to concern us. So let's talk about those reactants and products. Where is the energy in reactants? Look at kinetic energy, energy of motion. There's vibrational energy, there's rotational energy, and there's translational energy, which we talked about earlier in the earlier video. That energy is all added up in an individual molecule, and all those individual molecules in the system are added up to make what we call the internal energy. It's this internal energy that is a sum of the work energy and the heat energy and the translational, rotational, and vibrational energy. That's the total energy of the system. Again, we need to compare the system as reactants to the system as products. However, we cannot measure that energy. We can't stick a thermometer in that measures temperature, not energy. We can't stick, in fact, any meter in. What we can measure is changes in energy. We can measure how energy is different from the reactants to the products because we understand that energy must go somewhere or come from somewhere. And that we can measure. We can measure the amount of energy released by the reactants when they form the products. In other words, there is less internal energy in the products than in the reactants, and that energy goes from the system, those reactants and products, to the surroundings. Likewise, if the reactants have less energy and more energy is taken into the system, again, adding internal energy to the products, we have a change in energy. That is going to come from the surroundings. And we can measure again the amount that comes from the surroundings. We're going to focus, though, now on the relationship between those reactants and those products. And we call this energy reaction, or the change in energy, delta H, or change in enthalpy. This enthalpy, in addition to the entropy, will add to the entire amount of energy that we're going to look at. But right now, we're going to focus on this enthalpy. And we're going to look at two specific examples. We're going to look at an exothermic example, where energy of the reactants is released because the products have less energy and goes into the surroundings. Energy exothermic exits the system to the surroundings. And we're going to look at an endothermic reaction. Endothermic, where energy enters, is how I remember it, into the system from the surroundings. When it enters into the system, it's added to the reactants as they rearrange to make the products, and the products have more internal energy than the reactants. Endothermic. Here we have an example of what is an exothermic reaction. This is the combustion of ethane to produce carbon dioxide and water. This is exothermic. As we know, things that are burning give off energy. Why do they give off heat energy? Well, because that energy is going from the system to the surroundings. And so we feel the surroundings because we're in the surroundings. And so we can depict this in this graph. We see the potential energy of the reactants, that energy, that internal energy of the reactants is greater than the energy of the products. The change in enthalpy is this amount. We can calculate this as enthalpy final minus enthalpy initial. Now we can't actually measure this, but we know this is the change. And if you think about this, the final has less, so this is going to turn into, in an exothermic reaction, a negative amount. Let's make up numbers. Let's say this is 1 and this is 2. 1 minus 2 is negative 1. So exothermic will always have a negative change because there's less at the end than there is at the beginning. And when we do this reaction, we can measure the change in enthalpy is negative 1428.4 kilojoules. And this is per reaction, which in this case is per mole of ethane. But we would label this as delta H of reaction, RXN for reaction. We understand this is a stoichiometric relationship. In other words, if 1 mole of this reacts, we will produce or release 1,428.4 kilojoules. That negative sign isn't really negative energy. It just tells us there's less at the end than there's at the beginning, so it's released. Again, this ethane, 1 mole of it combusting, will produce 1,428.4 kilojoules. Now, mind you, 7/2 O2 will react to produce that as well. It's a stoichiometric relationship, and this number can be put in the ratio of the coefficients. This reaction here is photosynthesis. We know in plants, when light hits a plant or a leaf or chlorophyll, carbon dioxide and water combine to produce glucose and oxygen. This is a reaction we're adding light energy. It's endothermic. In other words, our reactants have some amount of energy, and energy is added, and it's stored as internal energy in the products. It comes from the surroundings, light from the sun, adds to and recombines these molecules, and is now part of the internal energy of the products. These products have more energy, and in this case, our change in enthalpy is going to be positive. Again, we have added energy. This is an endothermic reaction. Now, interestingly, we can look at this another way. We can look at the reverse of this reaction. And if we have the reverse of this reaction, we literally have the energies reversed. In other words, the things that used to be our products are now our reactants, and they have the same amount of energy they had no matter which side it is on. The products in this second reaction, this exothermic reaction, have the same amount of energy that it had as reactants here. But now the products have more energy than reactants. And we go ahead and we metabolize this glucose, C6H12O6, in our bodies, and we get energy out. Again, this is simply the reverse. This is an exothermic reaction. And in this reverse reaction, the exothermic reaction is a negative delta H. The reactants have more than the products. But literally, the delta H is exactly the same for both these reactions. It's just that the signs are different. For the photosynthesis is 2,802.5 kilojoules. Again, it's positive because the products have more energy than the reactants. In the reverse of that reaction, the metabolism, it has a negative 2,802.5 kilojoules. Exactly the same amount, but in a different direction. Now, this energy is being released. It's an exothermic reaction. So we can see exothermic and endothermic are two different relationships. Keep in mind, exothermic means the reactants have more energy than the products, and energy is released from the start to the finish into the surroundings. And endothermic is when the reactants have less energy than the products. Energy is taken into the system from the surroundings to make the product. Again, think of them as the same thing, just in different directions, as in this example of photosynthesis and metabolism or cellular respiration.